going to talk about how VR's ultimate display, which has been a really long quest from the 60s, is actually, in my opinion, a continued evolution of the paradigms of computing, which are now so small computers that are no longer just in our pockets, but are coming into our bodies. So that's what we're going to talk about today. All right, so before this gets too abstract, I want to actually show you an example. This is work done at HPI. What we see here is a user in VR, and pardon, they're using like a really old school headset, but has all the modern functionalities. There's hand tracking involved, and they can walk in the scene, they can walk in the building, and they can see things such as a virtual wall. Now, we all kind of know what happens when you face a virtual wall. You can go and try out VR demos around us here at the beautiful festival, and you know that usually VR is just a bunch of ghost-like sensations. I can walk just right through a virtual wall and nothing really happens. In fact, VR right now hinges on the fact that you believe the visual realism of things so that your behavior is more or less common sense, not crossing through the wall. But if you don't, or if you just test it out, you'll see that it's, ghost-like thing. So VR right now is only really hinging the visuals. And as we heard today, we know it's kind of really, really hard to fully immerse one's just eyes. So we need to involve the whole body. What I want to show you is that this VR, though very normal seeming, right? Normal VR headset, nothing special, nothing big on the user's body, will lead to different behaviors. So let's watch what actually happens when this user tries to go through that virtual wall. You can see he's trying to touch the wall, but his arm recoils immediately. And in fact, he kind of like walks around and he realizes, I can't cross that place. I'm gonna go, this is like a button that he will press. And I'll show the rest of the video later. He'll press and unlock the next phase and open that door. What's interesting here, and this is what the talk is all about, is how does this work? I mean, there's nothing really special on his body, on his VR headset. How can it generate like the sensation and the force of a wall? And why is it so small? Like, why can't we see the trick immediately? And the answer is going to be that it's about integrating devices with the human body. Now, if we step back into the early days of VR, this is 1960s, there was this very beautiful paper, sort of a vision-like paper that Ivan Sutherland put out. And he also put out a series of displays that came to be sort of the first VR displays, or some of the first pioneering VR displays. And in this sort of vision, he lays out a very compelling argument of all the benefits we could reap from VR. We could get things that are so immersive, they're useful for training. I could learn how to do something in VR, like the type of things Joan was talking about, and then go back to the real world, and maybe I'm a better medical student or a medical profession, right? I could actually learn skills from one to the other, but only if that VR is a decent emulation of the physical world, meaning if I'm manipulating tools, that VR must have things like forces and etc. And though his displays were very rudimentary at the beginning, in his vision he lays out things such as, the ultimate display, he calls it, that vision, should serve as many senses as possible. That would involve things like smell or taste, and even kinesthetic, which is, fancy lingo for forces, right? So it makes sense. If I'm training how to do palpation and being a better surgeon in VR, because it's great for training, it's very safe as well, and I can replicate, I can do it 100 times. Well, if it doesn't have forces, it's not going to lead to a transfer of knowledge into the real world. So we need that kind of VR, and early pioneers of VR knew that very, very well. So where did we go from here, from the 1960s to today, which is 60 years of VR? I'm just surprised to say that. You've probably seen these graphics, mapping out the evolution of VR. Super fun, seeing Ivan Sutherland here in a corner and all kinds of headsets. And this is a commercial type of map. If you would see a more, research map, Anthony would be here all over the place in the 90s inventing all kinds of things. But this is a commercial type of thing. You might remember some moments here, like the first Oculus coming out, and many of us trying and being very impressed. I was, for sure, by that device. And I took the liberty to extend this map, and over here I just put a blob of everybody's making VR headsets. This was a nice moment, 5 years ago or so. Every company was very excitedly making their own version of a VR headset, and I was happy to see that as a researcher myself. And it seemed more or less, and I'm sure many of you won't agree with the ones I've put here, more or less we're settling on some big players that came out with headsets just in the last days, but also in the last month, in the last year, that are fantastic and do lots of cool things, so maybe that's it. The end of the talk, thanks Lucas, and that's it. We've reached the ultimate display. But all of you know that's really not even close to what Ivan set out with smell and taste and forces. I've never seen smell, taste, and forces in the Apple Vision Pro or Microsoft HoloLens or Orion, which obviously I haven't tested because it came out 3 days ago, and the Apple Vision. None of them have that. None of them will lead to situations when I'm training VR physically and learn something that I can then transfer to the real world. They're visually really impressive. I've tried at least 3 of the 4, and I can say they're impressive visually, but not bodily impressive. And so the question really underlying all this is like, what's so hard about this? How come we've conquered displays, we've conquered all the engineering needed to make very small tracking systems to track the hands, to track the room, but we just can't seem to make the same amount of progress at the same speed for touch and forces and temperature and smell and taste and so forth, right? So let's start with forces just because that's what the VR wall is. A wall is just a moment of a lot of force that I can't penetrate through. So why can't the headset provide that amount of force to the user's body, to the user's legs, to make the VR feel less ghostly and more immersive? So let's pinpoint that moment, and let's rewind a little bit the history of robotics, the history of interactive computing, and you'll find out that, this was solved once and like really beautifully using a type of device that you could also call a robot arm, but more typically we call this an exoskeleton, that is just a bunch of motors that can resist the force of your body. So if I play this video, you'll see this user, he's happily in VR, not wearing a headset, but this is the simulation. He's rolling a ball up and down the incline, and as he pushes the ball up the incline, the motors, they force against his body. It's harder to move. That simulates gravity acting on the ball. The ball feels harder to move. This is a really, really like realistic kind of device. He's smiling because, it just feels real. If this was the training, you would then go up to roll balls up the hill and you would like feel, wow, this is, I trained over there. I'm better at this task. So why can't we have this? Why does the Vision Pro, or what's the newest one, the Orion, why does the Orion not ship with this in the box? And the answer is kind of obvious, but it's because the priorities have shifted tremendously. The priorities here in modern VR are small devices, untethered, mobile, powered by battery, no cables. The tracking system is included in this thing, which I never thought I would even see it. When I started, the trackings were very complicated. But this is the opposite. This is tethered to the wall, tethered to a power source. It actually is tethered to the wall for 2 reasons. One, it's very heavy, and 2, Newton's third law, it must push against the wall to provide a counterforce, right? That's Newton's third law. For every force, counterforce. So it's very hard to combine these two when these two sort of have gone in different trajectories with different optimization goals, mobility, extreme realism. So my question is there a way to bring some of these benefits of this amazing device, don't get me wrong, really, really exciting. I've tried things like this and they're just mind-blowing, but have everything else we've grown to like in today's modern VR, right? Like untetheredness, lightweight, unencumbered, right? And don't forget, this person is fully attached with these exoskeletons. They can't even shake your hands anymore. They can't even put the very VR headset on if you're having to grab the exoskeleton. So how to make these things convenient, less cumbersome, yet have the same output force? If there's any mechanical students in the room, you might be like, oh, I can just make the motor smaller. And then you run through your head and go like, that's true. But if I make the motor smaller, although there's less weight and less battery requirements, I also reduce the output force, and I can't do a wall anymore. I can't do training anymore. I don't have the same capabilities in the haptic device. So the key issue here is really that we're doing a lot of things hoping that the laws of physics and the laws of mechanics behave in the same nice way that Moore's law, which is the reason why computers get smaller, smaller, and smaller. We can just pack more transistors in a small space. But these two things don't work in the same way. Moore's law so far is giving really, really tiny devices. Motors don't obey Moore's law. You make them smaller, they're like, well, very little force. Okay, so here's one approach that I've started to explore actually during my PhD. What if we, instead of using motors to push the body, integrate the hardware in the user's body? In this case, let's use electrical muscle stimulation as a way to actually get the user's body to move. And this is not a technique that I've invented or people in VR have invented. This is a long history of medical rehabilitation since the 60s, And maybe some of you might even have experienced muscle stimulation where you go to the doctor, maybe you have your leg in a cast and your leg is potentially atrophying by being in the cast after breaking your leg or something. They'll put these electrodes, they'll dial some knobs, and rebuild a little bit of muscle tissue. Here, we're not giving the knobs to a doctor, we're giving the knobs to the VR application that says, I need a force right now, let's stimulate the body. And what happens is if you stimulate with a tiny, safe amount of electricity on the 2 electrodes on the top side of my arm over there, what happens is this. The wrist sort of moves involuntarily and automatically up. So now the VR is able to displace parts of your body. The VR is able to control parts of your body. Not just input, this is now the VR outputting. In playing that game, we can now turn the body into a force actuator. And so we can return back and explain what the force feedback device was. And again, like Lucas said, this is work that I've done at HPI with my former PhD advisor, Patrick Bowdish. And you can understand what's happening. He's wearing all these electrodes, and the VR is sending the force commands to the system and saying, generate a wall here, propel his hand backwards. Actually, he pushes the button now. It's actually really hard to push this button. You have to like, make force, and it clicks at the end. It gives you even like a little click. There's some projectiles being fired at him. He like deflects them, but as he deflects them, there's an impulse. His arm flies backwards. And in this final room, which is kind of a crowd favorite when I gave these demos at like SIGGRAPH and other conferences, I actually returned back to that idea of gravity. So he picks up these cubes eventually. When he picks up the cubes, what is going to happen is that his arms involuntarily go down, and he has to voluntarily kind of go up. And these 2 forces are in opposite directions, and they sort of feel like gravity. So we're able to generate force feedback, and yet the device is so small that if I would like roll down my sleeves, there would be no device. You wouldn't even see it, right? So that's much, much smaller when you juxtapose it with this mechanical approach of the exoskeletons, of any robotic approaches. So in fact, if you can only remember one thing from this talk, from this keynote, I would say it's this slide. The idea, the core idea that I'm trying to pursue here to push VR into a more mobile and yet more immersive form factor is, what if instead of adding more electronics to every single VR headset to produce forces externally, like if you want to produce the force of a wall, you go and ask yourself, okay, what thing do I add? A motor, and you add a motor, and it turns out it has to be a big one. What if we just go out to the world and see what's the minimum set of components we could find? Minimum set. And we stop there. That are sufficient to trick the user's biology into internally generating that sensation. The desired sensation, like the thing the VR programmer is thinking about. And in that case is force. Okay, what's the minimum set? 2 electrodes, tiny safe medical stimulator, done. And now put that with the VR simulation, send the force and like, let's get the wall feeling like a force. Okay, so that's the thing that you should remember, is this sort of like approach of actually putting less electronics and putting more electronics, because our body turns out to have, and the body has been a really nice theme in this session today, like our body has a lot of methods to generate the sensations that we need to feel. I wanted to just show what's inside one of these devices, because it's not going to be a super technical talk, but I reckon people would enjoy seeing what's inside. And so you can see there's nothing really special inside of one of these devices. This is one that I made a long time ago, more than 10 years now, during my PhD or before maybe even, and has a microprocessor inside, like a little computer inside, has some wireless capabilities so we can receive information from the VR that says, please generate me a wall here, generate me some force here, there's a punch over here, etc. And at the core sits this medical stimulator, the same that you would see in the clinics by the doctors, except instead of being a doctor controlling it, it's the VR that uses these digital circuitry to control it. There's batteries, and in the end, most importantly, there are electrodes that connect to the user's body to deliver the stimulation. Now, if there's engineers in the room, you're probably as excited about the slide as I am, because there's like a secret in this slide, which is from here to here, the entire left side is what we call solid state electronics, which means stuff that we can make really small for nothing. That's what the things that abide to Moore's law are solid state electronics. So this is big because I was a really bad engineer back in my PhD years. But my PhD students, like Lucas was saying, they're so much better. You want to see the equivalent device made by my PhD student, Jazz? It's this. I'm not joking. This is equivalent circuit for all this thing, electrodes, wireless, Bluetooth, everything, stimulator. and puts in the nose. I'm not going to explain why I would want to stimulate the nose in this talk because it's not about VR, but if you want, you can ask me later and I'll show you some fun videos. But it's the exact same device, right? So the electrodes are the only thing that is not solid state. We need the electrodes to cover whatever area, the nerve system of the user we need to stimulate. It's a muscle, it's fairly big. It's the nose, is very small. If it's the brain, it's very small, so forth, so forth. But it can be made really, really small, which is very exciting, and you'll see much more smaller miniaturized devices through the rest of the talk. All right, now what's fun about this is now we have a new type of device. It is very small. It produces forces different from the mechanical exoskeletons. Let's see if there are new applications that we can come up with. Because it's just so small, we can apply it in situations where we probably would not be wearing an exoskeleton. So I'm showing you something in VR. Let me show you something in augmented reality, right? So augmented reality, very similar, though I'm superimposing content in the real world. So this is sort of like IKEA simulator for choosing your couch and buying a new couch. This is a virtual couch, although it is a physical space where she's putting the couch. This user is dragging the couch, this virtual couch, but as she's doing that, she's actually feeling the forces and the boundaries where the couch is at. She actually feels the friction by the muscle stimulation as she draws the couch through the floor. More importantly, when the couch hits the real wall, and remember this is a virtual couch, she feels she can no longer push the couch forward because the muscle stimulation is preventing her from doing that. So she can actually figure out how this couch is going to fit. She figures out how the space is going to look. For us, it doesn't look very exciting, but from her view, it's like really cool red couch. HPI has cool red couches. All right. I'm going to fold all this stuff about, force feedback into this little chapter. We can talk more about that later if you're interested, and go on to Ivan's next challenge, which was, what about temperature, right? If I'm in VR, be a social VR around a fireplace, it's not going to feel realistic if it doesn't feel warm like a fireplace would feel. And in fact, we've done studies where we put people through these types of VR simulations, a training in a desert or a hike in a snowy mountain. And if you don't turn on the AC, like the real room AC up or down, they look at you and go like, really? Like, this is not very realistic if you're telling me this is a desert and I'm not sweating. So people have done beautiful things like this, by the way. This, again, I'm juxtaposing it for the sake of argument, but this is very, very effective. People put a heat lamp on top of you as you are in a VR desert. You really start to sweat because the air around you is so hot. And it's just one of the most immersive things I personally have tried, right? My body's super involved to the point that thermoregulation kicks in and I'm producing sweat. Now, obviously, I could ask the question again, why does the Meta Quest X does not ship with this? Well, because the battery of the Meta Quest would drain if you turn a heat lamp on it with a kilowatt power per second. You could do the same with an AC unit. So obviously, we want to explore something smaller, less energy, more convenient. And let's see how the answer is, again, to integrate with the user's body. This is work by my PhD student, Jazz Brooks. So you see here a user in VR. She's actually in front of a fireplace, and she feels like the environment is kind of hot. But if you look at what she's wearing, this is a weird device. This is not a temperature device. She's in a controlled temperature room. Nothing in the room is changing temperature, and yet she feels slightly warm. What's actually happening, and oops, I jumped over something here, is that, I don't know if you can actually see it. Let me play the video again, because I hope you guys could see this part. It's nice. Is that we're projecting a little amount of a chemical as she inhales. And I'll superimpose a little graphic so you can actually see, because the chemical is so small and we atomize it in little pulverized puffs. They're so small you can barely see it in the video right there, and you can't still not see it. And she inhales that. And you're probably thinking, what does inhaling something and smelling, olfactory and all that has to do with the sense of temperature? Nothing. My skin feels the temperature of the room. End of story. What does the nose have to do? If you zoom into the human nose, you'll find, just like in the lining of our cells of the skin, what you have is cells that detect temperature. So they react if the temperature is like above 45 or below 10, and they fire and tell your brain, it's really hot, it's really cold. However, and you know this, you've tried this, all these cells have another gateway, another entry point. They're chemically stimulated. If you eat capsaicin, which is that main ingredient in chili peppers, right? If you go to like the Indian restaurant and eat some really spicy food, you feel really hot. Now, contextually, you know what's happening. You look around, there's food, and your brain goes like, okay, hot because of food. I've experienced this before. But if you go inquire to that particular cell, it just was triggered. It doesn't know if it's chemically triggered or, temperature triggered. It just reacts and fires and tells your brain. In the absence of that cue, because you are in VR and we're not showing you spicy food, this thing is actually, once we purify it, it doesn't smell like capsaicin anymore. You just feel hot. So the trick here on how she feels hot is that she's inhaling a little bit, a minute amount, microliter dissolved of capsaicin, and she feels like the heat of that furnace. Now the room is going to be blown open by like a gust of wind, gets really cold, and we do the opposite trick. We switch into a chemical that triggers another receptor, and you've all experienced this, eucalyptal or menthol. You take a breath mint, a chewing gum, so refreshing. Like, it's refreshing because it physically triggers the cells in your oral cavity that get triggered. Those are called the trigeminal receptors, trigeminal cells. And so she's walking around outside and gets colder and colder because she's outside, and you emit eucalyptal more frequently. It's really fun. If you ever come to the lab, I would highly recommend asking Jazz to try this one because it's kind of crazy realistic. And then she finds the backup generator and goes back into the room. I won't play the rest, but you can watch any of these videos entirely. These are longest sequences on YouTube if you're interested. Now again, by juxtaposing the two, you realize that all we're doing is an illusion. There is no temperature changing. It's just telling your cells what internal sensation to generate. All we really need to do this is a microwatt of power, a little quarter of a watt, to really just pulverize. And then you can smell those chemicals. There's certainly other, even more power-efficient ways to deliver that chemical into the nose. What I want to say, though, is that it's the same story as you've seen before, right? What's the minimum set of components we need to internally generate the sensation of hot or cold? Well, it's just talking to the receptors, to the cells that already do that in your brain that generate hot and cold. Again, we can keep moving from challenge to challenge, and you'll see that the answer kind of keeps integrating with the body. This is a simulation of like sort of training how to, deal in a situation. If you spill a chemical in the lab, something that my students have to do every year, as they're training how to operate in such emergency situations, and this is a VR training of that. You accidentally spill a chemical, what should you do? You actually should wash your hands first, then your eyes, and only then the wound. If this doesn't feel real, if it doesn't feel like touch and an emergency of touch, almost painful touch, people are like, yeah, VR training, sounds cool, let the wound be there. I'll wash my hands later. So, again, turns out the answer can be the same one, can be to directly speak to a receptor of your body that generates the touch sensations. This is actually work by Jasmine, one of my PhD students as well, in collaboration with Jazz, who you've seen before. And I think this will start playing in just a second. There we go. This is called chemical haptics. And what we actually do is the same approach you've seen before for the nose, but we apply it to the entire cell. So the device that Jasmine is wearing here on the arm, but she's also wearing one in her cheeks, actually. She cannot see it because of the VR headset, is a device that allows her to feel super strange, very, very immersive, rich sensations in the virtual reality. Well illustrated by this example here. So she's in a simulator.
Nuclear reactor overheating. Please report to control room immediately.
She needs to find where the nuclear reactor room is, and she's using this arm device in VR to see the map, open doors, etc. And of course, nuclear reactors overheating is never a good thing. There's a big explosion, and her arm device goes crazy with electrical interference and sparks and so forth. And here, instead of using the canonical type of simulations people do in VR, which is maybe vibration or electricity to make you feel like something is tingling, what Jasmine does is she, again, passes a chemical. There's a chemical, I don't know if you can see a little snaky chemical going through these tubes. These tubes are open to the skin, so the skin is slowly absorbing the chemical, and this has a chemical called sanchul, which is also a food spice, and creates a feelable vibration. What's really cool is that she can just change the chemical and she gets a new sensation. So in just a second, she goes outside, it's very cold, she changes the chemical from sanchul to menthol, and in her cheeks is going to pass menthol, and it's like Chicago cold level of like blasting cold. Menthol is really strong, it's actually stronger than eucalyptal in terms of the cooling that it kind of activates those cells to do. We can do lots of other sensations. You've seen the warming before as well. We can do things like numbing even. And of course, the one that I was showing you about for the training, we can do cinnamaldehyde. which creates a kind of strange stinging type of sensation, almost like painfully stinging. Again, the trick is the same, right? You could go and find individual devices. People have engineered beautiful haptic devices that create skin sensations, but you would come up with a constellation, the whole body would be full of very crazy haptic devices, or you can try to just ask the user's body to generate those sensations by talking to those cells specifically and saying, please make me a vibration here, please make me a heating here. Now, I do want to flag something that I think this audience will enjoy, which is something we do here, and I feel like we all do in VR because we can get away with it, which is in VR, when we want to create haptic sensations like touch sensations, skin sensations, etc., everything is fine. We can cover up the body part where we want those sensations to arise. Like over there, we cover up her arm, all was fine. However, she can no longer use her arm to feel something because her arm is now covered by that device. This is how we came to the idea of VR gloves, which we're sort of like all very okay with, and especially mainstream, the companies are all very okay with. In fact, if you Google for VR glove, there's like tons of them you can already buy. And Meta, of course, is working on one. It's a very, very cool device. And this is all fine. Like if you really apply this to VR, everything works out. And just for the fun of it, I took the VR Summit poster. I hope that's okay, Art. I took the poster, and let's see what happens if she's wearing a VR glove to touch that little flying dust. All good. We put a glove on her with vibromotor actuators per finger. Her fingers are now covered, but that's all she's feeling. Everything in VR is generated. It's all fine. You could argue that's going to be a little bit hard to remove the headset if you have a big glove with so many actuators. They're kind of clunky. But besides that, if somebody else puts the headset on her, it's going to work out. Let's try the same thing in augmented reality. You all know augmented reality, same thing except we can see through. Great. So this is a device by Microsoft, very cool, especially for kind of like Microsoft HoloLens, for type of work situations. So this person is having a Zoom meeting while she's also repairing this engine. Maybe they're collaborating on how to repair this engine. If she wears gloves and touches the, hang up the Zoom call, she will feel a zzz. Great, more usability. She feels the device as she's touching it. Fantastic. However, if you're wearing gloves, I can guarantee you cannot fix this engine and manipulate tools because you lose all the dexterity needed to do that. Turns out we even tried, and people can't even put the VR headset on, if they're wearing gloves. They can't even shake someone's hand. The dexterity goes down by a factor tremendously. You can't even type on your keyboard. So what I'm saying here is that, funny enough, and my talk is not going to stop the companies from working on gloves. They should do it. This is going to come out. This is going to be great, but it's going to make us all realize the difference between being sort of contained in VR and being free in AR to do things in the real world. And unfortunately, this is not going to translate well into AR. So one of the things we've been doing in the lab is to ask if these ideas of using the body as an actuator, leveraging the body rather than putting more electronics on it, can solve this problem. Could I make someone feel a touch on their finger pad without covering up the finger pad so they can still type on a computer keyboard? And at the beginning, when we posed this question, we laughed at ourselves and said, no, that's a paradox. The receptor is there, so we need to put something there for the person to feel like they're touching in that location. There's no magic thing going on here, except we realize that every single cell is wired from the brain to the receptors, and so maybe there is a way. So hold on a second, and let's see this demo here. This is one of my former interns, Arata, kind of posing here as a participant in a study that we did where people could actually climb in this mixed reality, and I call this mixed reality just because it has physical objects. I'll show you something in AR just in a second, but this is also AR in the sense that this rope is real. He's in a training gym in mixed reality, training with real ropes, but physical kind of walls, virtual walls. So his hands are unencumbered in the sense that he can grab the rope, no problem, feel the edges, climb all the way to the top, so he can now finally start bouldering and climbing. And the virtual holds on the walls are all virtualized, but he feels them. He actually feels even the shape of them, like, oh, this one is like rounded, this one is spiky, I should adjust my grip, and so forth, so forth. But if you look at it, there's nothing in his palm. All the hardwares are on the back side of the hand. And what we're actually doing is a little bit of a neuroscience kind of hack, which we strategically place these electrodes. in locations where we know that the nerve from the brain, is going through and kind of passing over close to the upside of the body before it like shoots down and connects to this side. And we intercept and generate the sensation on the backside, but when you ask people where do they feel it, 98% or 7, you have to look at the paper for the number, I think it's 97% of the times, they say it's in the front, right? So we like trigger that sensation from the back. And you can do really, really fun things in mixed reality. This is one of my favorite applications. Again, if you come to the lab, please try this one. You're kind of molding, sculpting with clay in mixed reality while also kind of going with instructions and just imagining trying to do this while wearing gloves. I mean, we've tried and it was really, really, really hard to even get the clay out of the bucket, much less like make the cute teddy bear according to what the virtual model is telling you. You're supposed to feel it, and you can actually feel the haptics of the virtual model to see if the two are aligned and if you need to put more clay here or remove clay there. It's a really fun demo. All right, so I'm going to also fold this idea of the body becoming a tactile actuator and go to our last challenge, which was, can we figure out taste? And taste is a really, really difficult one. This is almost where, me and my students kind of threw the hat down and be like, oh, you can't do taste. This is just, what a nightmare. Like the sensations, the biochemistry is all really complicated. So much that what people actually do in VR, I don't know if everybody tried a VR with taste, is to just use food, real food as props. So you actually eat a virtual food like you eat a lemon and they give you a physical slice of a lemon. And that's cool, but I'm like, well, that defeats the purpose of VR. The purpose of VR is to generate things cheaply. If I need N props for N foods, that's not going to be very scalable. That's not going to be very exciting. I wonder if I could have one prop just to have a real sensation, real like chewiness, real explosion of taste in the mouth, but then somehow cheat my way into making one food feel like many foods. And that's what we do with this project, more recent one called taste retargeting. Maybe some of you have heard of haptic retargeting or redirected walking and like things like that. This is taste retargeting. So what's happening here, this is again work by Jazz Brooks, one of my PhD students, is a user eating props. She's eating blackberries. And in VR, she saw a blackberry. This is a survival game we made where you have to eat to survive. And later she finds a lemon. So this time she picks a lemon, but notice this is just blackberries. She's eating a slice of lemon, and yet somehow the whole experience feels just like she's actually eating a lemon, although she's eating the blackberry in real life. It's only virtually that it appears to be a lemon. We've tried just the visual illusion, didn't work. Check the paper for details. It's very, very unimpressive, the visual illusion. But somehow this worked really well. And actually Jazz got an award from the jury when they tried the demo at the conference. What actually happened is before she ate the lemon, the device she's wearing on her mouth, on her lips, you might see little lip cuffs over there. This device, just before she ate the lemon, so about the time she finished eating the first blackberry, activated and started delivering a chemical that we call a taste modulator. These taste modulators, and you'll be able to see just for a second the liquid passing through the tubing. This is just for you to be able to see the liquids are actually colorless. Can selectively change taste perception. It can, for example, take out sweet, take out salty, boost the umami. They can kind of go there and hack your taste perception. It's not the food that changes, it's your taste buds responding. And so in this case, we use a thing called lactazole, remove the sweetness. What does a blackberry taste if it's not sweet? Well, it's acidic. It's kind of like a lemon. And on this one, people rate it like almost as a real lemon. It kind of goes down as you try to push off a little bit to the extreme. But this one, they really buy that it's a lemon. They like almost 100% of realistic on the lemon. But you can do all kinds of things. I think in just a second after she eats the lemon and gets convinced that it is a lemon, you'll see her kind of going through transforming if I remember correctly, the blackberry into a strawberry. That's probably my favorite transformation. It comes like a party trick. It uses a chemical called miraculin, which is actually sold as a party trick, but we dilute it very small. Oops, you don't see it anymore. You can see it here. And then at the very end, we reduce everything, and it feels kind of just plump. And you should go on YouTube because people react like, whoa, and they're eating a spider. It's just like the plumpness of the blackberry exploding and the gushing things inside. And people actually kind of believe it. So to sum it up, the idea here is how can we walk these modern devices, VR devices, super convenient. And if you look at the things, these are all modern VR headsets, small things that we're not adding anything big like an exoskeleton. How can we make those devices go closer to that vision of ultimate display by really involving the body, right? Integrating more of the user's body in the experience. And yes, things like smell and taste will have to be there. Things like temperature are absolutely crucial. And of course, forces, because everything we do in real life is about fighting forces. So if VR doesn't have forces, it's never going to work, especially as a training simulation. All right, so I'm just going to conclude now and give you some takeaways, things to think about. The first one, and this was one for myself too, it's kind of fun to think about this. We're used to seeing the VR timeline like this, right? Oh, cool, all the inventions that happen in VR looks really disconnected. Just like, how did we jump from Nintendo Virtual to the Oculus? What happened there? There must have been something. Like, how could Palmer Luckey develop something that Nintendo couldn't develop? Nintendo's a massive, giant company full of really brilliant engineers. And the reason is because we're just looking at the timeline of VR. We're not looking at timeline of computing and the evolution of technology and computing. So if you actually put here how historically people interacted with computers, things start to have a little bit more context and explanation. So over here, kind of like first VR arcades and first cool VR consoles, they were really, really cool. It's just ahead of their time for sure. Is the time of desktop computing, a time when computers and users were stationary, computers were still kind of big, so no wonder VR was going to be an arcade that you go to and play there and then go out of. It made perfect sense. And still, these computers were not portable, but like this changed the world entirely. Like desktop publishing is completely reformed after desktop computers came out, right? People writing newspapers in computers and the internet and everything. Like it changed the world despite of the fact that it was still not portable. So now we see this next generation in a new light. And by the way, the Oculus Rift coincides beautifully with mobile computers coming out. In fact, those who know that if you take the Oculus Rift apart, you kind of just end up with an Android device inside that is kind of all taken apart. Is the screen, is the accelerometers, which were used for this rudimentary head tracking at the beginning. And turns out that was mass-produced because phones had accelerometers. And so the whole thing is starting to gain much more traction as we see it like that. And again, these devices sort of unleashed untethered VR because they had to be untethered themselves for other reasons, right? So I can put them in my pocket and access information on the go. And so VR sort of becomes untethered. These are very different looking from the previous stuff that all had cables and consoles to connect to. And of course, we keep going, and now it all, again, I think makes a lot of sense. Sort of the first time the little bubbles collide. This is the user bubble and the wearable bubble sort of touching, and wearables are this really weird kind of device that kind of straps onto us, and so you start to see like the Vive trackers, which a lot of you I saw in your slides, or the controllers that also strap to our arms, or literally this week, this Orion device came out from Meta, which has an armband that uses electromyography, so your muscle movements are being used, and all of these things are just strapped to your body. And that's only possible because the things we do with wearable devices are very different from the things we do with mobile devices and desktop. They are connected to our body 24/7, so they afford new capabilities. So the story here is that every time there's a revolution in computing, the VR folks are smart enough to find a new capability to put into VR. And so what I think we should all be thinking about is what happens next, right? What happens with this evolution from, this can start earlier, in infrastructure like computers, like really like back in the days in the 60s, computers, only one room was a computer. This is called mainframe computing. Desktop, mobile, wearable, what happens next? And you don't have to buy my story, but you should definitely think of what happens next. I think these bubbles are getting eerily close together, and we should start to look at that overlap between the two and see what happens when the technology integrates with the body. And the devices that I'm showing you today are just intentionally created to show you that, intentionally created to borrow parts of the body for input and output rather than adding more technology. And maybe, who knows, like that little meta thing that came out this week with muscles as input is a little part of this integrated story, because now your muscles are part of the thing that controls the actual device, and so forth, so forth. They're part of the hardware. It's not even just output movement. It's literally part of the hardware that controls the device. All right, part two of these takeaways is that, we've talked about touch and forces and some other fun senses that are often overlooked, but there's so much more, right? Here's another example of what you can do once you have extremely miniature actuators like the muscle stimulation. This is, again, work by Udai. And what you see here is a person doing a fire training simulation in augmented reality. This is my lab. They're learning what to do if there's a fire that breaks out in the lab. And they miss the next step. The next step is to go and grab the fire extinguisher, which is under the table. And in this case, the muscle stimulation kind of takes over and forces their head to rotate and see the fire extinguisher and go and grab it, right? So we're changing the point of view. We're changing where you're looking at in real time so that people have like a physical memory, like a muscle memory. It's over there. And they memorize that feeling where it actually is. We're actually studying whether muscle memory works like this or we're just confused. But I also invite you to watch the rest of this video because the simulation is going to guide him on how to leave the room, how to do the fire escape, and all these things, which is something that is very hard to do when there's an actual real fire, which has happened in my lab too. Obviously, we're not the first to say, hey, let's move someone's head and move their viewpoint. Our colleagues in neurology and medical rehabilitation have been doing this, again, with beautiful exoskeleton devices. What I'm asking is, again, this is probably not going to work with the VR optimizations for portability, convenience, and everything. Perhaps something like that could. So we're just seeing the use cases, how they change when we have a much smaller actuator like that one. And it turns out this difference between a neck motor and a neck muscle stimulation are not the only differences we've seen in size and also in power consumption. You saw the same story with the arm motor and arm muscle stimulation with the chemical and the heat lamp. Turns out usually when we do this trick of integrating with the body, we end up with smaller things and more power efficient things. The other part that I'm kind of excited about is asking the question, how far can we push this, right? Could we have, for example, one haptic device that replaces a bunch of people have done things where you're like full VR suit full of motors and vibrations and you can feel sensations in the whole body. Turns out they're really heavy and hard to wear, but the sensations are just amazing. Could we have one device that kind of does it all and we don't need to wear such a heavy kind of instrumentation? And so maybe another way to ask this question is how far can integration go? Can it go to the brain? And so here you see a project from this year called Haptic Source Effector, also by my student Yudai Tanaka. And what you see here is a user in VR, and he just got hit by a projectile, and he felt a tactile sensation from the projectile. And now he's actually going to fire back to the enemy, kind of posing this gesture. A projectile comes out of his hand, but actually what's happening is that the VR headset is instrumented with a neuroscience device called a transcranial magnetic stimulator. This is a coil that generates an impulse that can stimulate your brain without having to implant anything inside your brain. So once we generate that impulse, the impulse will kind of tell his body that that area that we're stimulating is the area responsible for hand sensations. So he'll feel like the projectile is coming out of his hand. He'll feel like a tactile sensation in his hand, though he's wearing nothing in his hand. The only thing he's wearing is a VR headset, which happens to have a coil on top. Now what we're going to do is move that coil to another location, to the location in this brain responsible for feet sensations, or for foot sensations in the case of one foot. And when he gets hit by that projectile, again, little magnetic pulse in his brain in that area of the motor cortex that is kind of responsible for that foot, and he feels, whoa, something hit my foot, although there was nothing in there, right? He's only wearing one device, although he feels sensations in about 17 individual parts of the body. Now, last kind of moments of the talk, a lot of the things I'm talking about are VR training and VR augmentations of things you might already be able to do. I'm not showing you details of this work, but we do a lot of work on how can people train better with muscle stimulation. We've done things like people doing two drawings at the same time. One drawing is muscle controlled, the other drawing is voluntarily controlled. As you can see, the muscle stimulation is not great at drawing. Piano playing, that's great. People like it a lot, or guitar playing. But these are things that people know how to do. You just don't know what the next key in the piano melody is, and the muscle stimulation goes like, I know which one it is. Bing, and you go like, great, thank you. It's just extending abilities that you already have. But over the past couple of years, we started asking the, I think, harder question, which is, what about new abilities? Like things that your biology isn't even ready to do, wasn't evolved to do, right? So we've done a number of projects here, including speeding up someone's reaction time. This one you can find in the Guinness World Book of Records, which is kind of cool, that old school book we had when we were kids, with muscle stimulation, giving people a sense of stereo smell. But I want to show you this one, which is a work in progress. There's no paper, there's no anything. But from the last couple of weeks, and I promised Lucas I would show this one to him as well, which is how to speed up your reaction time by not forcing you to do something, but just helping your brain to be a little bit faster. So this is a person, this is work by Yudai Tanaka again. This is a person using the transcranial magnetic stimulator, that little thing on the brain that stimulates your brain with magnetic pulses, non-invasive. Here the system is off, and she's going to try to do like a really fast hitting of a ping pong ball in an esports game. And she's going to miss it because it's really, really fast. It's like the type of thing where like 8 milliseconds make all the difference. And here we're going to turn the system on, but the system is working at a very, very low intensity. If she would just be standing still and the system, she wouldn't move. All the system is doing, the transcranial magnetic stimulator, is to heighten a little bit the electrical activity in that area of the brain, so it's like easier to excite. It's already pre-excited a little bit. It's like repeating the same movement over and over. You're kind of exciting that area, so you're kind of faster at reacting. So we just do one small pulse before she does it. This pulse does nothing but pre-excite that area, and she's able to actually be about 10, 8 milliseconds faster. Depends a lot on the person. Some people are really, really fast, and she gets that ball. But it's her that does everything. She decides to move. She decides when to do anything. We're not forcing her to anything. We're just helping her become permanently kind of faster. All right, and last but not least, and this will just be a really, really quick slide, I've shown you a lot of sort of body integration that has everything to do with neurons and chemical cells and more the neuroscience of human-computer interaction and more the human of VR. But I think you can take this idea of human-computer integration to different levels of VR as well. So for example, just to show you very small teasers, we've done work, this is work by my student Chen Yuan Tang, my PG student, where he uses a VR haptic device that has no battery. It is the user moving around in the room that is charging the VR device all the time. And he actually conducted a study and people did not notice after hours of using this that they were the ones charging the thing, because in VR you can craft a story in a way that you kind of hide that you're charging the device. Really, really beautiful work. Alex, also a PG student working at Meta right now, he's done some work on integrating physical terrains and temperature sensations in VR. She's holding part virtual object, part real object. How do you do this sort of integration with physical props? And Yujie, who was my master student, now a PG student at Stanford, worked on integrating distractions in VR. If I was in VR and somebody opened that door right now, a gust of wind would come in and I would be like, oh, this doesn't match the VR experience. Whoa, immersion broke. Yujie's device detects the gust of wind and changes the VR world in real time to also have a gust of wind, and you go like, whoa, that's super immersive. I felt wind when there was wind in VR. Wow, what kind of haptic device is this? It's nothing. It's just that she leverages every distraction in real time to integrate in VR, and people sometimes don't even spot that she's doing that. So really, really cool work. All right, final slide. This is my team. They are the people who really did the work. I am really just sort of channeling it here for all of them, including some of our alumni who aren't with us, but you saw their work and their faces today in the talk. And I'd be happy to answer questions after this as we're just chilling around the festival and trying demos. And I want to make a big shout out for the organization team, especially Art, for bringing us all here together in physical space.